Let's take a look together at a very important topic here called the difference quotient. So, first of all, what I want to talk about is we've been discussing about the average rate of change. So, let's say, for example, I draw a function. I'm going to call that arbitrary function here I'm drawing. I'm going to call it f of x. And what I would like to do in this function f of x is find out how much the function is changing from some value a to some other x value that I'll call a plus h. Now, I know that a plus h, and the reason I'm calling it a plus h is that it's h units away from whatever my starting point a is. So I want to know what the rate of change is from a to a plus h. Well, okay, I can go in here to f of x at a, and clearly the ordered pair at a would be a, and the y value you could call f of a. Now at a plus h over here, of course the x value is a plus h, and the y value is just whatever f of a plus h is. Now, if I'm trying to find the average rate of change there, that can also be given by the slope of the line connecting those 2 points. Notice, if I ask you to find the slope of that line, you could say, oh, slope of any line, that's the change in y over the change in x, or y2 minus y1 over x2 minus x1. So notice what I've done here is I can say, well, the slope of the red line, it's going to give the average rate of change. It's going to be the change in however many y values occurs in that distance of hx values. So it's going to give me the average rate of change from x equals a to x equals a plus h. I can say the slope of the line is the exact same thing. Now, the notation I'm going to be using for average rate of change, and we use it in calculus as well, is AROC, average rate of change. The average rate of change from A to A plus H. Well, that's going to be my function evaluated at A plus H, that's the y2, minus the function evaluated at the initial x value, A, that's your y1, over the change in the horizontals, a plus h minus a. We already know they're h units apart. I just put that in the denominator. Now, whenever we're discussing these in our class, we're going to really be honing in on the average rate of change. That's why I say here, in algebra and pre-calculus classes, we focus on the average rates of change. This concept is going to form the logical foundation of probably the most fundamental concept in all of calculus, called the derivative. Derivative is nothing more than an instantaneous rate of change. So the way that we're going to get an instantaneous rate of change out of an average rate of change, and think about it in this drawing up here. What if I said, instead of the average rate of change from this point to this point, what if I said, guys, I want you to be able to tell me how fast the function, or what is the slope of the function at the instant of x equals a. And you might say, well, in order to find slope, I always have to have 2 points because I need a y2 minus y1 over x2 minus x1. You do. Okay, but if I wanted to know exactly how fast the function is increasing or decreasing at the point A, which is going to be given by the derivative at A, all I would have to do is take that average rate of change function, and let's say that second point gets ever and ever closer to the first point. So what if A plus H, what if it was right here instead of up here, and my point was right here? The line would be slightly negative in that case. Well, that would be a better approximation of what's happening at A. Well, what if A plus H moved even closer to A, and I had 2 points on a curve pretty close together, and I found the slope between those? That would even give me a better approximation. Well, how good is good enough? Well, you actually need that limiting value as h is going to approach 0. We need the distance between those two to be as negligibly small as possible. So there needs to be an infinitesimally small distance between the a and the a plus h. That's what this is saying down here. Now, you won't have to worry about this in a pre-calculus class, but I just wanted to show you the foundation, where this is leading to. We would say the instantaneous rate of change of f of x at x equals a. It's called the instantaneous rate of change at x equals a, also known in Calc 1 as the derivative. Derivative notation, we say f prime, the derivative of function f evaluated at a. It would equal the function I have up here, just where the distance between those two x values becomes negligibly small. So the limit as h approaches 0 of the y2 minus the y1 over the change in x value, as that change in x value gets infinitesimally small, so it has to approach 0. Now, all I'm saying at this point is that that is a beautiful formula, gorgeous formula that you're going to be seeing soon in the next class in our Math 1910 or calculus classes. Now, I do refer to what the derivative would be in some of the problems later on, just to give you a little taste of what's to come. Let's first look at a difference quotient problem here. I'm asking you to use the difference quotient. Use this formula right here. This formula is called the difference quotient. So f of a plus h minus f of a over h. And again, please remember, this is just the change in the y values over the change in the x values. Slope is always the change in y over the change in x. So I can say, well, all right, I need to know what the slope from any value x equals a to any value x equals a plus h is for the function f of x equals 7x plus 5. Now, unlike this would be a cubic function up here. Unlike that cubic function that always has a different slope given any x value, or it has a different rate of change, this one, we know it has a constant rate of change. Y equals mx plus b. This linear function has a constant slope of 7. So I already know the answer, and you can see it right there, before I work the question. But let's just show how the formula is going to work out within these. I can say, all right, the slope is going to be given by f of a plus h minus f of a over h. All right, well, what is f of a plus h? That's just telling you to evaluate your function f of x. In the place of x, you're going to plug in an a plus h. So I get 7 times the group a plus h plus 5. This is my f of a plus h. And you'll notice I always bracket that off to show the separation. This is my f of a plus h. Now, minus f of a. Well, f of a is just your function evaluated at a instead of x. So we get minus the group 7a plus 5, all divided by h. Now, in that numerator, that 7 would distribute through the group a plus h in that first one, and I would get 7a plus 7h plus 5 minus 7a plus 5 all over h. Now, I want to talk about some common things that always happen whenever you simplify out the difference quotient. For any of these polynomial functions, and we know the linear function 7x plus 5, it's just a polynomial function degree 1. Anytime you have a polynomial like this, and I would say in every problem, not just polynomials, the terms of f of a plus h and the terms of f of a always cancel. They will never combine, never. So no surprise here. You can say, well, 7a minus 7a cancels, 5 minus 5 cancels. They will always cancel. And so you say, well, then the only term I have left in the numerator is the 7h. Well, I guarantee you, you're always going to have terms left that have a factor of h. Why? Because that h in the denominator needs to cancel with the factor of h in the numerator. And you'll see, well, 7h over h, I can eliminate h and cancel out the h's here and get my overall slope of 7 for this problem. So you say, well, hey, that was a pretty beautiful problem. Yeah, but that one was an easy one. Let's look at a more beautiful one. So if I ask you to simplify the difference quotient for a quadratic, f of x is equal to x squared plus 2x minus 5. Now, what I'm wanting us to do is to use your answer to show how we can find the average rate of change from 2 to 10. So now, if we didn't want to do the difference quotient, you could find the average rate of change from 2 to 10 without even doing this by just saying, well, the average rate of change from 2 to 10, it should be my function evaluated at 10 minus my function evaluated at 2 divided by the change in x, which is going to be 10 minus 2. So you'll see I did that on down here, and I applied the difference quotient. Let's go ahead and show how the difference quotient can be simplified in this expression. The algebra in these problems and how we simplify is important too, so make sure you understand and see what's happening. I need to take f of a plus h minus f of a over h and apply it to this formula. Well, f of a plus h, well then I can say I'm going to have a plus h quantity squared plus 2 times a plus h minus 5. This whole group is my f of a plus h. What do I want to do with that? Well, I need to subtract it by f of a. What is f of a? It's just your function evaluated at a. So I say minus the group f of a squared plus 2a minus 5. All of that's divided by h. And then I can say, well, all right, I'll square out this first group. Please remember, a binomial squared is always a trinomial. A plus h times a plus h is going to be a squared plus 2ah plus h squared. I distributed the 2 through the second group, and I have my minus 5 still. I didn't change anything in my second group. I'm still subtracting all of f of a, and all of this is still divided by h. Now, please notice what happened in the next step. I can say this average rate of change from a to a plus h is going to simplify to every single time the terms of f of a and f of a plus h must cancel. A squared minus a squared goes away. 2a minus 2a goes away. Negative 5 minus a negative 5 cancel. So then you need to be thinking, well, what terms are left over? This term didn't cancel. I have 2ah plus h squared plus 2h. Now, I mentioned this in the last problem. I guarantee you, any terms that don't cancel out, I promise they're going to have a factor of h left in the numerator. And in fact, I'm so confident that that's always going to be the case. You could go directly from this to this and just say, well, I know any term that is not going to cancel out always has to have a factor of h. I can pull that h out and say, oh, well, here's the first term that didn't cancel out. If you factor an h out of it, you have 2a. I guarantee you this term didn't cancel out. When you factor an h out of it, you have an h to the first power left over. This term didn't cancel out. You're going to have, when you factor out the h, you'll have the plus 2. And then you can say, all right, we can eliminate the h's cancel in the numerator and denominator, and you're left with 2a plus h plus 2. Again, I'm just dividing out those two and left with the trinomial expression there. Now, stepping away from that average rate of change difference quotient formula, so this is a formula for the average rate of change. That's what the difference quotient gives me. But now, let's say I wanted to find the average rate of change without using that formula first. Okay, I know the average rate of change, it's just the change in y over the change in x. So it's going to be f of 10 minus f of 2 divided by the x values, 10 minus 2. I would always prefer to put the larger x value first in these expressions. What if you said f of 2 minus f of 10 over 2 minus 10? No big deal, as long as you're consistent with the order in the numerator and denominator. So if your numerator starts with f of 10, your denominator better start with 10. Now, when I'm simplifying this, I can say, well, f of 10, that's just telling me to plug a 10 into my expression up here. That's where I'm getting 10 squared plus 2 times 10 minus 5. Now, minus f of 2, that's going to be 2 squared plus 2 times 2 minus 5. I know that the first term is going to give me 100 plus 20 minus 5. That's a 115. I'm subtracting from that 2 squared plus 2 times 2. That's 4 plus 4 is 8 minus 5 is 3. So I have 115 minus 3. That's y2 minus y1. 115 minus 3. Well, the distance in the x values, they're 8 units apart. So I can say, well, I'll be dividing that by 8. My numerator gave me 112. 112 over 8 is 14. Now, this answer for the average rate of change did not involve me using my difference quotient. But let's say I did want to use that difference quotient now. So this is just me trying to show you that that difference quotient does have a purpose. So if I wanted to use the difference quotient to find that same average rate of change between 2 and 10, you've got to go back and think with me about what A and H are in the problem. Please remember, A is always your initial X value. So in this problem, A is 2. Well, what is H always equal to? H is always the distance between the two X values. So you just say, well, then clearly H is 8 in this problem. That's the same thing I divided by 8 right there. So now I'm asking you to use the difference quotient with A equal to 2 and H equal to 8. Plug that into your formula right here. The average rate of change between 2 and 10 is going to be 2 times A, 2 times 2, plus H, which is 8. A lot of students will make a mistake and say, well, shouldn't I put a 10 for that? No. H is the distance between the two X values, which is 8. And then I'll have my plus 2 at the end. No, please notice you'll have 4 plus 8 is 12, plus 2 is 14. We get the same average rate of change answer either way. Now, if I wanted to carry along this example towards where you'll be going with it in a calculus class, instead of finding it, so calculus is not concerned with average rates of change necessarily. We always want to know instantaneous rate of change. At some moment in time, how fast were you driving? At some instant on the curve, what is the exact rate of change at that moment in time? Okay, so let's say I wanted to know the instantaneous rate of change or the instantaneous slope at x equals 2. Well, in calculus terminology, we would call it the derivative evaluated at 2. And you'll say, well, it is always the limit as the distance between your x values approaches 0. And again, please remember why I'm setting that h going to 0, because if that second point gets pushed infinitesimally close to the first point, then I'm finding the average rate of change between 2 points extremely close to one another. That's going to give me a really good estimate for an instantaneous rate of change. So I can say, well, then the instantaneous rate of change is going to be when you let h equal 0 in this expression, and you know that you're wanting to know the rate of change at 2, so you just plug in 2 times a becomes 2 times 2, plus h, which is going to become 0 plus 2. So I have 2 times 2 plus 0 plus 2. Well, the instantaneous rate of change at 2 is going to be 6. So that means it's going up with a slope of about 6 units at the instant of 2. Now, I could also show you that here on the calculator. Let me show you that here. This is pretty cool. If I went in and graphed out x to the second plus 2x, and then I have minus 5. Let's say I graph this on Zoom 6. All right, here's my function. And I'm interested in what's happening at x equals 2. So I'll say, well, f of 2 here. F of 2 is 3. Now, instead of just f of 2, I would like to know what is the exact rate of change of the curve at this instant of x equals 2. Well, notice you can go second calculate, and remember the slope formula is the delta y over delta x. It means the change in y over the change in x. Well, if you want the infinitesimally small change in y over the infinitesimally small change in x, otherwise known as the instantaneous rate of change of y with respect to x, you just choose number 6. And you say, well, I need to calculate the derivative or the instantaneous rate of change at x equals 2. And then it will tell you, hey, your instantaneous rate of change there is 6, meaning it's going up 6 y units per x unit at that instant in time. Now, clearly, the slope gets greater than that because the average rate of change from 2 to 10 went from a slope of 6 all the way to a slope of 14, because this quadratic function is going to get steeper and steeper and steeper as we're moving from x equals 2 to x equals 10. Okay, excellent problem there. Let's look at even a more fun one. So you're thinking, okay, that one was a pretty good problem. What if we want to see a fraction or a rational function done with the difference quotient? That's what I wanted to do. And I got a little slanted with my writing, and I apologize. Says for number 3 here, I'm asking you to simplify the difference quotient for f of x is equal to 1 over 3x plus 5. And then I'm wanting you to take the answer that you get for the difference quotient and use that answer to find the average rate of change from x equals 3 to x equals 5. Okay, so here's my difference quotient formula, f of a plus h minus f of a over h. How does that formula apply within this function f of x? Well, f of a plus h tells me to plug in a plus h everywhere I see an x. That's what I've done right here. 1 over 3 times a plus h plus 5 minus f of a, it's just saying it's the same thing as f of x, except you put an a in the place of x. So 1 over 3a plus 5, all divided by h. Now, the only thing I've done from this step to this step is I distributed the 3 through that group a plus h to get 1 over 3a plus 3h plus 5. And now, in simplifying this, and any time you have fractions inside of a fraction, I'd like you to remember the best algebraic technique is to get rid of those fractions inside the fraction by multiplying by the least common denominator of any denominators in there. Well, there's no common factors between 3a plus 3h plus 5 and 3a plus 5. So I need to multiply by both of those factors in both the numerator and the denominator. Now, when I do that, things are just going to work out so much better. Now, I remember the difference quotient formula, it's going to give me the average rate of change from a to a plus h. So I say the average rate of change from a to a plus h is equal to. Well, whenever you multiply this least common denominator in the numerator times the first term, this 3-term expression is going to cancel this 3-term expression, and you'll be left with 1 times the binomial 3a plus 5. That's where that came from. And please remember, it's the group 3a plus 5. I'll still keep the minus. And then when I take the second term and multiply it by these two products, I can say, well, the 3a plus 5 is going to cancel with the multiplication of 3a plus 5 over here. But I'll still have that group 3a plus 3h plus 5. I bring that down. The most common error I see algebraically with students in these problems is they will not put a group around the second term, and they'll end up only subtracting the 3a, and then they'll think that the 3h is added, and they'll think that the 5 is added. That is not the case. You're subtracting the product of 1 times that entire trinomial. Has to be a group. So now, numerator and denominator is set. Keep in mind the denominator I just left in factored format. It would never be to your advantage to distribute h through these, because we know in the final answer that h needs to cancel out. So please leave it as a factor in the denominator. In your numerator, please remember what I said about the terms of f of a and f of a plus h. They always cancel. So you say, okay, 3a minus 3a goes away. 5 minus 5, no more. So you're just left with a minus 3h, or a negative 3h, I should say, in the numerator. Once you get to that, then you can say, this is the step in the problem that's my favorite to say. This is where we eliminate. And you know, hey, if I can eliminate in the problem, I'm done. So I write my final expression and say, well, my numerator is -3. My denominator is just going to have these two factors. Nice answer. Now, that nice answer, I think it looks nice, but I could see some saying that looks pretty ugly, but there's beauty in that ugliness. So I'll say, all right, that's my average rate of change formula. So now let's work with it. So on this page, I'm saying I'm still working with that same function. If I tried to find the average rate of change, now this is, I'll use the formula in a minute. This is just using the base function. If I said, what if I don't want to do that and I want to find the average rate of change from 3 to 5 without depending upon that formula? Well, I could always go in and say it's just f of 5 minus f of 3 divided by 5 minus 3. And then say, well, okay, f of 5. That means you're replacing a 5 in the place of x in your function, 1 over 3 times 5 plus 5, minus f of 3, 1 over 3 times 3 plus 5. F of 5 is going to give you 1 over 15 plus 5, that's 1 over 20. And then f of 3 gives you 1 over 9 plus 5, 1 over 14. We divide all of that by the distance between your x values, which you can see here, they're 2 units apart. So now I take that numerator, 1 over 20 minus 1 over 14 over 2. And what I did here is I found the least common multiple of these two. I could say, well, they both go into 140. So if I multiply by 140 over 140, it's going to get rid of these fractions inside the fraction. I multiply 140 into the first one. 140 divided by 20 is 70. Minus 140 over 14, it's going to give me 10. My numerator is going to be 7 minus 10. My denominator is going to be 2 times 140, or 280. I'm going to get negative 3 over 280 for my final exact answer there. Now, that's a gorgeous answer. Let's now show what would happen if we used our difference quotient solution to get towards that average rate of change. Now, please remember, if you're trying to find the difference quotient solution, you say A is always your starting point. A is 3 in this problem. H is just the distance between your two x values, so H is 2. So that's why I said let's use our difference quotient answer right here with A is equal to 3 and H is equal to 2. So I took this expression here, and everywhere I saw an A, I replaced it with a 3. Everywhere I see an H, I replace it with a 2. So I have negative 3 over 3 times 3 plus 3 times 2 plus 5. And then 3a plus 5 becomes 3 times 3 plus 5. In your first group, you're going to have 9 plus 6 plus 5. That's going to give you 20. Second group is going to be 9 plus 5, or 14. And you see, hey, this is negative 3 over 20 times 14, which is going to give you negative 3 over 280. Now, in this case, if you're thinking, well, it was just as easy to do it this way as this way. The nice thing about this difference quotient formula, though, is I could give you any x values that I wanted. I could say, well, hey, find the average rate of change between 200 and 296. You just say, oh, okay, well, A is 200 and H is 96. Plug that right into this formula, you get your average rate of change just like that. It's a formula that works for any two x values. Now, if I tried to think of the calculus terminology here, and I say, well, what if I ask you what the instantaneous rate of change at x equals 3 is? And you say, well, all I'm going to have to do to find the instantaneous rate of change of 3, and the notation for that is it's the derivative, and it just looks like an apostrophe on the f. It stands for f prime of 3, or the derivative of f evaluated at 3. And you'd say, well, all it is this average rate of change formula. You're going to be plugging a 3 in for A, because A is the value of x you're interested in. So you're going to plug a 3 in for that. And you don't want any distance between A and the next value of x, so H is 0. That's why I can say, well, this is negative 3 over 3 times 3 plus 0 plus 5, 3 times 3 plus 5. These are just 14 times 14 now, and you get negative 3 over 14 squared, which would be negative 3 over 196. The fact that the average rate of change is less than the instantaneous rate of change at 3, all that tells me is that this function is decreasing between 3 and 5. And you can see that at 3, it's at a height of 1/14, which is like 0.07142857. At 5, it's only at a height of 1 over 20, which is 0.05. So it's reduced down 0.02142857 units over these two x values. That's why the average rate of change is less than the instantaneous rate of change at the initial part of this interval. Beautiful stuff. Now, some of what I just said is more calculus terminology. So if you're okay with just finding the average rate of change and plugging them into the function, that's okay for pre-calculus, but I wanted to give you just a little bit of insight as to what's coming in our next gorgeous class. Number 4 here. Let's say I ask you to simplify the difference quotient for f of x is equal to the square root of x minus 2. And I'm asking you to use the answer to find the average rate of change between 6 and 11. Okay, so here's my difference quotient formula, or average rate of change formula. And I can say, well, if I try to plug in f of a plus h, then everywhere I see an x, I replace it with an a plus h. So I get the square root of a plus h minus 2. Now, minus f of a, which is just the square root of a minus 2, all divided by h. At this point, I'm wanting you to remember our goal in this problem is to cancel out that h. Well, you're never going to be able to cancel out that h, at least not unless you don't algebraically manipulate that numerator. As soon as you see the 2 square roots up there, you should automatically be thinking, ding, 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 ding. The way to algebraically manipulate that is to multiply by the conjugate. The conjugate is the exact same 2 roots with the opposite sign in between. So we're going to multiply by the square root of a plus h minus 2 plus the square root of a minus 2 in both the numerator and denominator. You must multiply by an understood fraction of 1. Now, when I multiply by that in the numerator, by definition of a conjugate, you only have to worry about the first term times the first term and the last term times the last term. The middle terms always cancel. So you have, well, any square root times itself is just what's inside to the first power. So I have a plus h minus 2, the group to the first, minus the group square root of a plus 2, sorry, square root of a minus 2 times square root of a minus 2 is the group a minus 2. A negative times a positive is minus the group a minus 2. And I can say, all right, now my denominator is h times this group where we have both of these square roots added inside of it. Now, if you recall what I've been saying, whenever we simplify these, the terms of f of a and the terms of f of a plus h always cancel. If they're not canceling, you're doing something wrong. Well, a minus a goes away. Negative 2 minus a negative 2 cancels. And so you say, well, the only term left in the numerator is h. That's wonderful, because now I can say, well, then the average rate of change from a to a plus h is just h over this factor of h times the sum of these 2 roots. I can then eliminate h, since I have a constant factor of h in both the numerator and denominator. Whenever that h divides into the h in the numerator, it leaves me a constant of 1 in the numerator, and then I have both roots in the denominator. Now, I can't simplify those 2 roots. You can't add the terms inside of a root like that, but I can still use that expression to simplify my average rate of change. So now, if I was trying to find the average rate of change from 6 to 11, and the way I would rather you do these is by using your difference quotient solution, so that's the only way I'm doing this one. If I say I want to find the average rate of change from 6 to 11, you just say, well, a is where your interval starts at 6. H, it's just the distance between your 2 x values, so that's 5. So you'd say, okay, I have a is 6, h is 5. Now, let's plug that into this function. So, well, it's going to be 1 over the square root of a is 6, h is 5. I get 6 plus 5 minus 2. And then over here, you'll have a is 6 minus 2. So you've got the square root of 11 minus 2, which is the square root of 9, and the square root of 6 minus 2, square root of 4. That's easy to simplify. You know that's just going to be 1 over 3 plus 2 for 1/5. We are 100% certain that the average rate of change of the square root of x minus 2 from x equals 6 to x equals 11, it's increasing at a rate of 1 y unit per 5 x units in that region. Okay, guys, hopefully this helps you out with the whole concept of the difference quotient and get you excited about what's coming in the future with that instantaneous rate of change. Now, we do find instantaneous rate of changes algebraically and letting the limit as h approaches 0 in the final step. So like, for example, in this one, if I let h equal 0, then I could say f prime of a would just equal 1 over 2 times the group a minus 2, because then these two groups would be the same if you could let h go to 0. But there's also shortcuts that you'll learn in calculus to kind of take some of the algebraic fun out of it. That'll show you how to get to those derivative answers without having to do it algebraically every single time. But the algebraic derivatives are fun too. All right, guys. So hope this helps with this section, and have fun working the difference quotient problems out of your book.